chemistry concept, and it basically deals with the consistency of atoms on one side of the arrow and the other side of the arrow. So we're going to learn the formula, we're going to learn the structure of a reaction, reactants, products, stoichiometric ratios, subscripts, and things like that. And if we think about it in the context of parts, we're going to get into limiting reagents. So if you had a pile of wheels, and you had a pile of frames, and you had a pile of seats, how many bikes could you actually put together? Well, you can only put the number of bikes together as the limiting component. So if I had 20 tires, and I had 1,000 seats and 1,000 pairs of handlebars, I can still only build 10 bikes, right? So we'll see that, and we'll see how limiting, but to establish limiting reagents, we first have to build on how we use stoichiometry, and we've got to then first build on how we actually balance a chemical equation. So we have the same thing on the left as we do on the right of the arrow. This whole thing of law of conservation of mass is from the 18th century with Antoine Lavoisier, and with that we basically know that we can his axiom was we may lay it down as an incontestable axiom that in all the operations of art and nature nothing is created, an equal amount of matter exists both before and after the experiment. Upon this principle the whole art of performing chemical experiments depends. So that was towards the end of the 18th century. Again, very crude apparatus that he would have been working with in his laboratory, but that's a very powerful axiom that we still hold true today. We haven't seen it violated. So remember, a law, we don't have many laws in science. The law of thermodynamics, the law of whatever you want to call it. A law is basically something we just haven't seen, the law of gravity. We just haven't seen a violation of it. Is it correct? Probably, but we don't know for sure. We just haven't seen it violated, so we call it a law. Right? And there are not that many laws in all of science, things that we haven't seen violated. So again, science in the way it works is very fluid. It morphs, it changes, and we get better ideas, we get better understanding through experimentation and through study. And so you can see that this one is one that has not been violated. So we in the chemistry community, we use this and we say that, okay, well now we can do rational and reasonable reactions, because we do know that we have the same thing on the left, or as the reactants, as we do on the right. The products, at least the atoms, are conserved. We don't change atoms. We change the compounds or the molecules, but we don't change the atoms themselves. Okay? So the mathematician Legrand lamented at the beheading of Lavoisier, it took them only an instant to cut off that head, but France may not produce another like it in a century. It's kind of a bummer, he got his head chopped off. Kind of a gruesome way to go. All right, here's the chemical equation that we're going to work with. We use a lot of different arrows in chemistry. The first arrow we're seeing right now is a double-headed arrow heading to the right. We will see equilibrium arrows, we will see retrosynthesis arrows, we will see future work arrows, we will see we'll see single electron, single-headed arrows. So this is our very first arrow. We use a double-headed arrow with a chemical reaction. And if I do have a double-headed arrow, it means that the reaction goes all the way to the right. Now we're not to equilibrium yet, we will get there, but again, that's what that's signifying, that I'm going to the right. This reaction does not go backwards. So once I take methane and I burn it in oxygen, it goes to water and carbon dioxide, and it does not go back to methane and water. It's a one-way arrow, okay? Cannot put Humpty Dumpty back together again. In fact, the only way you can take dead carbon and convert it back to living carbon is through photosynthesis, which we talked about. Yes?
I thought you could do it like high pressure too.
Go backwards?
No, I know, but it's like what's it called? It's when you run the current through the...
Yeah, you can do that way. But again, for this reaction, it is one way. Yeah, we can go backwards.
Right, but it's a different reaction.
Yeah, it's a different reaction. Got it. And that would have a new arrow. Yeah. Okay, so if you see a single arrow going to the right, it means that reactants on the left, okay, go to products on the right. That's what that's signifying. We should have the same number of atoms on the left of the arrow as we do on the right. So that's what this is showing you down here. We should have one carbon. Over here we better have one carbon, and we do. One carbon and carbon dioxide. Here we should have 4 hydrogens, and we see the 4 hydrogens. Over here we should have 4 hydrogens, and there they are, the 4 hydrogens. Over here we have 4 oxygens, meaning we should have 4 oxygen over here, 1, 2, 3, 4. So again, this is what we're going to work on, is the balancing chemical equations. We should have the same on the left as we do on the right. Sometimes they're tricky, sometimes they're straightforward, okay? You just have to work with them. There are different rules you might have heard applied. I don't think there's any real standard way to do a balanced chemical equation. To me, it's just trial and error, and eventually they solve. Okay, they take a little bit of work. Some of them are tricky than others. Some are pretty straightforward. Okay. We also have the states of the molecules or the formula that we're working with. Okay, the states here are in green, and all of these are gases. So I have methane gas, I have oxygen gas going to carbon dioxide gas, and water gas. All right. We'll have gas, a G. We'll have a liquid. We'll have an L there. We'll have an S for a solid, and we'll have an AQ for an aqueous. So we want to know the state of the molecule I'm working with. So in this case, they're all gases. So if you see a G, of course, that is a gas. If you see an L, that is a liquid. And if you see an S, that is a solid. And if you see an AQ, that is aqueous. Okay? And those are really the four states that we work with. Aqueous will be when we're dealing with metathesis reactions or we're dealing with titrations down the road. Solids typically are for precipitates that fall out of solution. Typically a nice color, white, yellow, brown, brick red, whatever. Liquids, we'll see that comes into play when we're dealing with Arrhenius acids and bases. And then here we're seeing gases, and we'll deal with gases when we talk about the gas laws in our gas law chapter. Okay? So those are your states of the reactants and products. And that's very important to keep in mind. Now, coefficients are really important, and this is where we're going to practice with our stoichiometry. The coefficients tell me how many of those molecules I have in order to keep the molecule, the reactants and the products balanced. So the coefficients are the stoichiometry of the chemical equation. Those are my stoichiometric amounts. Those are what helps the left balance with the right in getting the right number of carbons, hydrogens, oxygens on the left as I have on the right. Okay? And that's really the anatomy of the chemical equation. So reactants, products, states, and then our coefficients or our stoichiometry ratios. Okay? Pretty straightforward. Now, notice that there's a difference between the superscript and the stoichiometry, right? The coefficient, and you can see that here. The coefficient tells me that I have two of those, whereas the two down here tells me that I have two of those. And that's what when we talked about the four locations, the four locations around the atomic symbols, right? We had the mass, we had the atomic number, we had the charge, and now we are seeing that we have this thing that we call the subscript or the number of atoms in that formula. All right, so that's when this one becomes important. So this is the one we're talking about with the subscript. This up here then is going to be the number of those that I have. Okay, number of the whole molecule. This is the number of the atoms, right? And so there's a very important difference between the stoichiometry and the subscript telling me that's how many of those atoms I actually have. All right. Again, I think this should be a review for everyone. Okay. All right, so let's look at a couple different balancing chemical equations, and let's just make sure we're comfortable with this, because again, we have a worksheet on this, but I'm going to move on into working with this at a little bit deeper level. So let's say I take sodium and I react it with water. Notice the states of those. I've got sodium as a solid, so sodium as a solid reacting with water as a liquid is going to be an exothermic reaction. That's going to be a very violent one. If you remember in lab with Jeff Wilson, who blew himself up, that's the reaction he did. Added metal sodium or added liquid water to metal sodium, and it exploded. So if I do take sodium solid plus liquid water, it goes to, notice, sodium hydroxide aqueous. And we'll talk about aqueous down the road. It just basically means they have ions there and hydrogen gas. So this is a very explosive reaction. All right? So you're adding water to sodium, and you're getting a very exothermic reaction and a big flash of the hydrogen gas going off. Okay? So what we want to do is we want to typically look at an equation, and one of the rules of thumb is save the atom or the element that's in more of the formula for last. That's just a simple rule of thumb. So when I look at this, I'm going to do hydrogen last because hydrogen's in 3 of these. And you don't have to do it that way. That's just the way I do it, and it works. Okay, so I'm going to go ahead and look at my sodium. I've got 2 sodiums. That's working out so far. I've got 2 oxygen. I've got an oxygen and an oxygen. Okay, that's working out pretty good so far. I've got two hydrogens, and one hydrogen. So now I have three hydrogens over here, and I only have two hydrogens over here. So one of the ways I can actually do this is to say, oh, well, I need a half of a hydrogen. But what's a half a hydrogen look like? Because remember, hydrogen is one of the 7 that's always diatomic, so you can't cut it in half. Oh, so what I could do is do what? Multiply everything else by 2. So if I just went 2, whoops, excuse me, which would make it 1. 2 times a half is 1. So 1, 2, 2, and 2, does it balance? Well, 2 sodiums, 2 sodiums. 2 oxygens, 2 oxygens. 4 hydrogens, 2, 4 hydrogens. It's balanced. So that would then be my balanced stoichiometry. And I would take and fill in that sure enough, to balance this, I have a 2, I have a 2, I have a 2, and I have a 1. And that would be a balanced chemical equation. Okay? Again, sometimes you just have to work at them. They're just little stubborn problems. And some of those are pretty difficult, especially when you have 3 products with 3 reactants. Then it gets a little bit crazy. Let's say we did propane. So propane looks like this. So there's propane. So how will we balance the chemical equation for propane? Well, again, in this case, I'm going to do oxygen last because oxygen is in the most of the formula. So I'm going to start with carbon. I have 1, 2, 3 carbons here. So I'm going to start with trying to put a 3 there. See how that works out for me. So I have 3 carbons here. I have 3 carbons here. So if I have 3 carbons here now, that means I have 3 times 2, which is 6 oxygens and 7 oxygens. Huh, that's kind of weird. Well, let's go to hydrogen, see if that helps us. So I have 3, 4, 5, 6, 7, 8 hydrogens. Over here I have 2 hydrogens, so if I put a 4 here, now my carbons and my hydrogens are happy. You tracking? So I have 3 carbons, 1, 2, 3, 3 carbons. I have 8 hydrogens, or 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Now I'm going to go my oxygen last, because I always save oxygen for, or the one with the most for last. So I have 4, and I have, how many here? 6, so I have 10. So how many, oops, sorry, that should be O2. Diatomic. So if I have 6 and 4 is 10, how many oxygens do I need? 5, and that is a balanced chemical equation. Okay? And again, you really learn those not by watching me, but just by doing them. That's why we're going to do those in our worksheet. Okay? Okay. So that's it for balancing chemical equations. Again, we'll work on that. Some on Achieve. I will upload Achieve this afternoon or tomorrow morning. So let's move on into actually using some kind of interesting calculations of different reaction types. So there's really 3 main reaction types that we're going to see in the course of this semester. We're going to see what are called combination reactions, where we take 2 atoms, or 2 different elements, if you will, in this case, and we're going to add them together. We're going to combine them. So something like a magnesium metal and oxygen gas is going to form magnesium oxide. All right, and again, we've worked with forming magnesium oxide from its nomenclature. Magnesium oxide, knowing magnesium is 2+, oxygen is 2-, therefore it's MgO. And so you can see that here. That takes 2 magnesiums for 1 oxygen to make 2 magnesium oxides. That is called a combination reaction. Very common in chemistry. A lot of rusting, a lot of tarnishing, and when metals add oxygen to them, they become the oxide. Some other examples that you might see is nitrogen and hydrogen. In fact, to form ammonia, which is a really cool reaction, you could take something like propane and react it with, or excuse me, that's propane, and react it with bromine, and it'll form the dibromide of propane. You can even take hydrogen and oxygen and add them together and add a lot of energy from that. If you could have pure oxygen, pure solid oxygen, or liquid oxygen and liquid hydrogen or whatever, and add those together, they form an incredible amount of energy. But those would be combination reactions because I'm taking 2 elements and I'm combining them to form a new compound, okay? There's decomposition reactions. Decomposition reactions are when one molecule falls apart. We'll see quite a few of these in our gas chapter. We'll talk about carbonic acid is a decomposition reaction. It decomposes. Calcium carbonate decomposes to, as you can see here, calcium oxide and carbon dioxide. Potassium chlorate, remember back to your nomenclature, potassium chlorate decomposes, and we'll actually do this lab, decomposes to potassium chloride and oxygen. And finally, sodium azide decomposes to sodium and nitrogen, which is exactly how an airbag works in your car. It produces an incredible explosion of nitrogen gas. If you ever have been in a wreck and have had an airbag deployed or seen someone that has, it's a very violent reaction. Actually, a lot of people get really hurt from those, but it's better than going through the window or getting crushed in the car. So kind of take bad for worse type of thing. But very, very violent reaction, very fast reaction, and again, it's a decomposition reaction. Okay. Combustion reaction. These are going to be basically oxidations. We're going to be adding oxygen to things. We're going to burn methane. We're going to burn propane. We're going to burn octane. We're going to burn decane. We're going to burn dodecane or whatever the compound is, benzene. They all burn. They're flammable. Toluene's a great one. But those are combustion. Typically, combustion is adding oxygen. Okay, and we're going to burn cellulose. We're going to take C6H12O6, add it to oxygen, and we're going to get a lot of energy, carbon dioxide and water out, and that's what we would have if we burn a log or start a fire or something like that. That's burning cellulose. That's burning sugar right there, and get a lot of energy out of burning sugar. Okay, so that's a combination reaction. Our last reaction are the more fun ones that we'll get into. These are going to be metathesis reaction. Some people have undoubtedly spent time memorizing the precipitates. I'll explain to you how that works. It is an act of memorization. But what we do with metathesis reaction is typically we're going to take two soluble compounds. So lead nitrate is soluble, sodium iodide, they're both soluble. You can tell they're soluble by the aqueous there. That tells me that it's soluble. When I add lead nitrate and sodium iodide, all the ions are completely what we call free. They're disassociated. When lead, though, finds iodine, it forms a sort of a covalent compound that doesn't like water, which is why it falls out as a yellow precipitate, and we call that a solid. So lead iodide is a solid, and sodium nitrate is still floating around in the water. Right? So that's a metathesis reaction or a precipitation reaction, and we'll spend a whole chapter on those, and very important reactions for us in a general chemistry course to understand the reactions of these compounds. Okay? Now, formula weight is taking the periodic table and now using the atomic mass units and turning it into something that I can actually use. If I'm going to calculate the formula weight of something like a calcium chloride, I know that calcium chloride takes 1 calcium and 2 chlorines because I've already worked through my nomenclature knowing that calcium is a 2+ cation, chlorine's a 1- anion. So if I asked you on a quiz, what is the formula weight of calcium chloride, and I spell it out, I don't give it to you as CaCl2. You have to know, oh, it's CaCl2. Why? Because it's calcium 2+, it's Cl1-. We cross multiply, we get CaCl2. Okay? Then I go to the periodic table, and I say 1 calcium atom weighs 40.08 average atomic mass units. 2 chlorine atoms, again, average, weighs 2 times that, 35.45 times 2. So that's why when I have this up here, I take 1 times the calcium, 2 times the chlorine, and I get the formula weight of calcium chloride. So that's how we use the periodic table to our advantage to know how much things weigh. When we get into the mole concept on Wednesday, we'll see that not only is it atomic mass units, but it's also grams per mole. Okay? So again, we're building on that idea of using those numbers off the periodic table. So the calcium chloride has a formula weight of 110.99 atomic mass units. Okay? All right. What about the molecular weight? Notice this is the formula weight. Formula weight is going to be for a metal nonmetal. Molecular weight is going to be for a molecule, which comes from a nonmetal nonmetal. So molecular weight, it's a molecule, it's not a formula. It's not an ionic compound, it's a covalent compound-ish. So with this, if I were to ask you the molecular weight of something like ethane here. Ethane has 2 carbons and 6 hydrogens. So again, I go to the periodic table, I multiply the 2, because there's 2 of them, times its atomic mass unit off the periodic table, which is 12.011. And I know that hydrogen is 6 of them, and it weighs 1.008 or 1.00794 if you want to be more precise. And so you can see that here we have 30.070 atomic mass units for the formula weight, or excuse me, the molecular weight of 1 ethane molecule, okay? Again, I would assume that's pretty much review for most people in this class. All right, now, 2 other things that we need to use in our calculations. How do I get the percentage composition, right? So I have to have a fraction that has to equal 100 total, 100%. So what fraction is each atom in this formula or in this molecule? So that's going to be the number of atoms times that atom's atomic weight divided by the formula weight or the molecular weight of the entire compound multiplied by 100. That's it. Number of atoms times that atom's atomic mass divided by the complete weight of the molecule of the formula multiplied by 100, and we get the percentage of each of those out. So for example, going back to ethane, ethane was C2H6. So I need to know the complete mass, which we calculated. The complete mass of that was 30.07. So I know I have 2, because here's, again, if you don't remember, here's ethane. Ethane looks like this. So ethane has 6 hydrogens and 2 carbons. Its total mass that we just calculated right here with the molecular weight is 30.070. So I have 2 carbons, so 2 carbons times 12.011 multiplied by 100. So I know that the percent carbon in ethane is 79.887%. Again, I think that's pretty straightforward. Number of atoms times the atom's atomic mass unit divided by the complete weight of the formula or the molecule. Okay? Now, this one's not straightforward, so please listen up. I know I'm going to lose some people in here, and you're going to be like, "What? What did I do?" So I need you to engage with me, okay? Because this one I don't want to get a bunch of random questions on how to do this, because these are not straightforward. So, if I know the percent composition of a compound, how do I take that and go back and get its empirical formula? And how do I get it from its empirical formula to its molecular formula? This is a little bit more tricky, so please stay with me on this. And once we're done with this, then we'll work our worksheet. Okay? So I can calculate the mass percent of the elements. When I do research and I come up with a novel compound, I have multiple novel compounds that I've come up with, I have to make sure they're super pure and they're dry. I don't want any impurities in there, I don't want any moisture in it. It has to be 100% that compound. I send it down to the Berkeley labs, and they have a way of actually burning my molecules and weighing how much water, oxygen, and carbon have, or excuse me, hydrogen, oxygen, and hydrogen, carbon, and oxygen have come off that molecule. They then send me a report back, and they say the compound you sent me has 12.31% carbon, has 27.44% hydrogen, has 37.02% oxygen. Okay, that will equal 100. Then from that, I can confirm that my empirical formula was the molecule that I think it is. It's one way that I can confirm I've made what I think I've made. The other way is using the NMR, the mass spec, a couple other techniques, but that's very important. So this is an experimental ratio that I get from a very high-end laboratory, and they're very expensive to do, but they're also very important to confirm I made what I said I made in a publication. Here's the key. Are you listening? You're going to get it as a percentage. It will equal 100%. So I am going to take that 100% and I'm going to assume it's 100 grams. That's all you're going to do. See that right there? Assume 100 grams. Because all of those percentages are going to equal 100%. So I'm going to convert that into grams. Simple. If I have 32.72%, it's 32.72 grams. Okay? Then I'm going to calculate the grams of each element. All right? How am I going to do that? Well, if I have 37.25 grams, I know how much 1 gram of carbon, I know how much carbon weighs, so I divide it by the molecular weight, or in this case, the atomic weight. Okay? Then we're going to divide by the common, and I'll explain this to you, the least common, or the lowest mole ratio, and that gives us an integer, or a half integer, or a third integer, and I'll explain that, okay? From that, then we can get the empirical formula. All right, like I said, these are not straightforward, but I'm going to work you through the steps. And they're really cool when you do them. Once you kind of get your first one, like, oh, that's actually pretty cool. So let's do an example. Para-aminobenzoic acid, PABA, compound that's found in sunscreens. It's composed, when it was burned at the laboratory, the report came back at 61.31% carbon. It came back as 5.14% nitrogen, came back as 10.21% oxygen, and 23.33%. Find the empirical formula of PABA. Kind of cool. What's the very first thing I'm going to do? Assume 100 grams. So if I assume 100 grams, notice I have 61.31 grams of carbon. I have 5.14 grams of nitrogen. I have 10.21 grams of nitrogen, and I have 23.33 grams of oxygen. Okay? Since I know that carbon, and you could do moles here or AMUs. It doesn't matter. I just have moles on this example, but AMUs, we haven't talked about the mole yet. That's Wednesday. It's the same number. AMUs or moles will be the same. So here, I have 61.31 divided by 12.011. This is how much carbon I have, how many atomic mass units of carbon I have, if I'm talking about just one molecule, or one molecule, divided by 12.01 atomic mass units or grams. So notice, I have 5.10 moles of carbon. Okay? Stay with me, that's all I'm doing. Taking the amount that I just assumed is from percentage to grams, dividing it by the atomic mass unit, or the grams, which is right here, 12.011. Jump down, divide 5.14 by 1.011, or 0.1007 or 1008, however we want to go down with that one. That gives me 5.09 moles of hydrogen in this. 10.21 divided by 14, which is the atomic mass unit of nitrogen, gives me 0.7288. 23.33 divided by 16 gives me 1.456. Okay? Now, we're not done. What you have to do now is you have to look at this ratio and say which one of those is the smallest number. And which one is it? Nitrogen. So now what I do is I take all of these mole ratios or atomic mass units, or actually these are still moles, and I divide it by the lowest, 0.7288. Okay? So, taking 5.105 divided by 0.7288, I get 7. Taking 509 divided by 0.7288, I get 7. Take 0.7, I divide it by itself, I get 1. Take 1.458 divided by the lowest, I get 2. So the empirical formula for PABA, para-aminobenzoic acid, looks like this. Oh, that's the structure. I'm going to give you the structure. So the empirical formula looks like this: C7H7NO2. Wow, isn't that cool? So you came up with the empirical formula. That's the empirical, not the molecular formula. I'll explain what the difference of that is. That's the empirical formula. I came up with the empirical formula based on burning it in a laboratory. So that confirms that I know the structure of PABA to be a benzene ring with a nitrogen and a carbon with a carbonyl over here. So this is the structure for para-aminobenzoic acid, para-aminobenzoic acid. So you can see that it's C1, 2, 3, 4, 5, 6, 7. C7, H, 1, 2, 3, 4, 5, 6, 7. Oh, we're getting there so far. N, 1 N, and 2 oxygens. Hey, it actually worked. It confirmed what I believed it to be. Isn't that kind of neat? So that's how we know structures. That's one way we can confirm that what we're talking about is actually what we're talking about, even though we can't see those molecules because they're so small. Okay? Question?
But with the empirical formula, you can tell if it's parent or what's the-
No, you can't tell orthogonal. No, no, you'd have to do that through NMR. Absolutely. Good, yeah. Okay, and you couldn't do that through mass spec either. Mass spec just fragments it so you get the same fragment of pattern. You have a little bit different IR, but other than that, yeah, you're right. Okay? Now, the other thing this doesn't do is this doesn't tell you whether that's the molecular formula, or excuse me, the molecular formula. Listen up. Empirical formula is the lowest denominator. This molecule could have been, meaning this molecule could have been C14H14N2O4. This molecule could have been C21H21N3O6. I don't know which one of those it is. I need more data. Because all the empirical formula does is it gives you the lowest common denominator, the lowest ratio. It could have been this, it could have been this, or even more, right? All I'm doing is, this is all multiplied by 1, this is all multiplied by 2, this is all multiplied by 3. So I cannot get the molecular formula from an elemental analysis or this combustion analysis that we did over here, this mass percent element thing. I have to have one more piece of information, and that is I do have to have the actual molecular weight. Okay? Just happen to know that is paraminobenzoic acid, but notice if we sent this molecule in for combustion analysis, if we sent this molecule in, which looks like this, if you're going to get into organic chemistry, it's propene, very important for polymers. What would my empirical formula of this be? Yeah, CH2, right? So when I do the empirical formula, when I burn this thing, this is the ratio I'm going to get. So the only way to know if this is C2H4 or C3H6 is to have one more piece of data, and that is to know the molecular weight. We get that through mass spec. So I do have to have a second piece of data to get the actual molecular formula. Okay? So we'll add to that as we go, but for now we're going to just calculate empirical formulas from combustion analysis. Okay? All right, so I think with that, yeah, okay, and this is what I mean. So empirical formula is not molecular formula. That's what I'm trying to explain over here, these things here. We have to know what my integer is, what the n is. So the n here is 1, the n here is 2, the n here is 3. Over here, that's n1, that's n3. So I have to know the number of actual units of that empirical formula I have to get the molecular formula. Sometimes it is the molecular formula, but not always. All right? And by doing that, we have to have the actual, we have to actually have the what we call the molecular weight of the compound. So let me walk you through this a little bit, and then we'll jump into our worksheet. So let's say we have something that has a molecular formula. Again, propenes right there, 85.63% carbon, 14.3% hydrogen, and 42.08 well, that's a typo, percent of. Sorry. I'm like, what in the world's going on here? Okay, because it only has carbon and hydrogen. So 85.63% carbon, 14.3% hydrogen, and it has a molecular weight. Listen, it has a molecular weight of 42.08. I got that through a second piece of information, mass spec, probably a high-res mass spec, and I actually send that in, and I get that data back out. I send in the compound, and I get it burnt, I get the combustion analysis out. I combine those two pieces, and I get the molecular formula. So follow how this works. Whoops, let me do it for you. If we do the molecular formula, the molecular weight for this, we have 1 times 12.01. We have 2 times 1.008. So when I add all that up, somebody want to do that for me real quick? What do we get? Anybody have a calculator in here? Anybody? Anybody do it? Now, stay with me. This is the empirical formula. The molecular formula, or the molecular weight, is 42.08. So I take 42.08 divided by 14.026, and what would you get? Somebody do it? Yes. So you get 3. Look at that. Telling me that all of these now need to be multiplied by 3, or C3H6, which is exactly what I know propane to be. Okay? So you need both those pieces of data. You need your percent masses through combustion analysis. You need your molecular weight through mass spectrometry. Okay? And with that, it's your turn. So